Okay, Tony, you ready to get all the answers right now since you get a second try at it? So what did you say is similar the forces in a cable? Here's a problem where we have a cable and the forces in a truss. And what was your answer?
I said you draw them away from the
Draw them
free body
away.
diagram.
Right, so if we're drawing a free body diagram of this point right here, this joint, we would be drawing it away, where if we drawing a free body diagram of the weight of the bucket, we would have a point where all the tensions connect. And when you draw a force away, what kind of force is that?
It's a force and tension.
A force and tension, right? And what is a force in tension or a force in compression? What is similar? One goes towards and one goes away, but what is their direction?
Away from the body. I think were you about to ask what a cable can't support?
Okay, sure. I'll ask that. Since you're bringing up that question, answer that. What could a cable not support?
Okay, it can't support compression.
Right. It could only support a tension, right?
Yeah.
But with a truss member, because it's a physical, hard, rigid body, a member is rigid, it could accept a tension or compression, right? But what's similar, let me give Tony a break. Tim, what's similar between tension and compression? What is the direction of that loading?
They're both kind of two force members as far as how you picture them in a sense.
Okay, great. So a member of a truss is a two force member. And you guys, from your interview number 2, a two force member means, Tim, you want me to tell me what's a two force member? What's the two? What's the significance of the two?
You have two points,
right,
at which forces are acting on.
Right. So we have two locations. So even though it's called a two force member, it doesn't mean that there are two forces. It means there are two locations where there are forces. And you could say the same thing with intention. When we're looking at this bucket being suspended, there are only two places where there are connections. So you could say really that a cable and a truss member are two force members. And Tim, what's significant about a two force member? What does it tell you about the direction of the force?
You're able to use it as one, like you could call it, say if it was AC, you could call it AC instead of having to break it up, and you're able to have less unknowns, essentially.
Okay, so let's say a little bit, I want something, we're gonna get to that too. But if I were to draw AD for tension, how do I draw it? If I drew tension AD, it would be from what and
pointing
to
away
what?
from the point where you're analyzing.
Right, so it would be drawn from A to D, right?
Correct.
Along the line of the cable. And
yes.
For the truss member here, where am I?
Man, I think that your video shut off on the, at least I can't see it on your document camera.
Yeah, it just shut off now. Okay, now it's showing again.
Okay.
So if I'm looking at this member, and let's call this AB, we know that if we drew it in tension, it would go from A to B. If we drew it in compression, it would go from B to A, correct?
Correct.
So Peter, what do we know about two force members then? What is the direction of the force? What's it along?
It's along the member itself.
It's along the member itself. So a cable, we know a cable always takes tension, and the direction of the force in the cable is away from the joint you're analyzing along the axis of the cable. For two force members in a truss or a two force member in a frame, it's the same thing. The force lies along the axis of the two force member. So some of the problems we looked at, okay, sorry, Are you getting dizzy from me spinning this around so much? You getting vertigo?
Not yet.
Not yet.
Except
Good.
for that, sometimes in frames, the two force members are bent. So it would be.
Good, and that's what I'm bringing up right now. Thank you for moving me in that direction, Maria. So let's find one. What pages were we on? 240, right? Weren't the problems, a lot of the problems we did 240? Do you remember from interview? You guys, do you remember?
No.
Yes, where there's like a frame or a member that can be replaced with just a.
Here, I have one.
Yeah.
Okay, so take a look at this. So we are on Miles. Miles, is this a frame or a truss?
Let's see. That would be a frame
How come?
because we got 3 forces on member ABC.
Not 3 forces.
More than 2.
No,
Uh,
we're not talking about the number of forces. We're talking about the number of locations that the forces
oh
are.
yeah. Yeah.
So member ABC is what, Miles?
It is a multi-force member.
Yes, and it's also, give me the number.
3 forces in different locations.
It's a 3-force member because the forces and the connections are at point A, B, and C.
Yeah.
Okay, Miles, what about BD? What is it?
2 force member.
A 2-force member, which means, can I replace this member AB that has an angle with a straight rod that goes from B to D?
If you wish to, yeah.
Yes, and I do wish to. Unless I had an angled bracket in my garage for free. Then I would keep it angled. But otherwise, if I had to pay for it, I would get a bar from B to D made out of the same material, and it's going to be cheaper because it's easier to produce and it's less material. It's going to weigh less. I'm going to have to pay less money to haul it to the site, although it's only 3 feet. Okay, so this BD here is a 2-force member because there are 2 locations where forces and connections are. I can replace BD with 1 bar BD. And the force, normally, Tim, I think what you were trying to say was ordinarily because B has a pin, we would put a BX and a BY. And because D is a pin, we would put a DX and DY. And that's for unknowns. But now that we know it's indeed a 2-force member, Myra,
Joanne, I'm a little bit confused.
okay, let's back up before I go to Myra. Maria, what's your question?
Why is it, doesn't it have it, isn't the A on the same member as BD? A.
No, it's probably maybe hard to see. I'm on page 200 in the textbook.
Okay.
Let me hold this. So there are 2 members here. One member is ABC. It's 1 bracket. And then another member is BD, which is another bracket. So there are 2 members on this frame.
Okay.
And it's a frame because ABC is a 3-force member because it has 3 locations where the forces and the connections, are. Member BD is a 2-force member. Can you see it better now, Maria?
Yeah, I can see it in my book.
Okay. So Myra, we were saying that BD, since it's a 2-force member, it could be replaced with a bar. And instead of having a BX and BY and a DX and DY as the unknowns at the pins, instead, what does it have, Myra?
It's just BD.
BD. So we just reduced this 2-force member. Well, we just reduced the reactions at the pins at B and D together from 4 unknowns to 2 because we knew it was a 2-force member. Okay, so it's a really important point. When you do frames, first take a look to see if there are any two force members. And I urge you to look at the overviews of each of our modules, because the overviews have a summary of every single thing that we've done. So now if we go back to our truss, up, every time I, you know why it stopped? Because Dave Reynolds sent me a text. Every time something comes in,
Tell him
Dave,
we say hi.
yeah,
Who's that?
he's the dean of the department.
Oh, that guy.
Sorry, dean of the division. All right, so what's going on now? Darn it. Okay, forget it. So trusses, we know that trusses are only two force members. So Matthew.
Yeah.
When we're solving and doing free body diagrams of two force members of trusses, which are only two force members, what is the direction that we put all those forces of each of the members?
We draw them in tension.
Right, we're drawing them along the axis of the member. Okay, so I believe everyone is on now. So I'm gonna start sharing so everybody's comfortable with the difference between frames and trusses? Give me a thumbs up. Everybody's comfortable with two force members mean when you say two or three force members, it means the number of locations on the member where forces or connections are. And for two force members, the force lies along the axis of the member, just as it does in a cable. Good? Okay, so now I'm going to share our Canvas screen. And let me get there first. Okay, so what I'm going to do first is we're going to go through what's going on the rest of the semester. And then we're going to do a review, and then we're going to have a quiz. Okay, so today, Tuesday, November 24th, and everybody's with me, right? Everybody hears me and is listening and watching what I'm doing? Okay, and if you could show your face, that'd be really great. All right, so today we're doing a review. So I'm going to skip that for now. But notice we're going to have, oh, I want to put something else in here. Okay, so we're going to do a review on, we're going to go over the steps again for solving statics problems that are both particles and rigid bodies. We're going to do an overview of trusses and frames, which we did a little bit already today. Of course, I will post the Zoom recording when it's ready. And then I'm assigning a project. So we are going to do a project, but it's very light. It's very fun. It's sentimental. It's getting you to be a little thankful for some special things you have in your life. And we're throwing in a little bit of statics. Okay? Because the project is worth 10% of your grade, and Rob and I decided that we were not going to have an intense project. You already have enough intensity in your life, but I wanted you to connect something special in your life to statics. So we're going to look at that in a little bit. Plus, I'm going to have a third interview, but the interview is going to be really an online quiz because I don't have enough time to meet with all 30 of you again. So if you notice, here it says the interview, and if you scroll down, you'll notice, okay, Thursday and Friday of this week, there's no class. But on Tuesday, December 1st, which is a week from today, is when you have your interview. And let me tell you what the interview's on. It's a 3D statics problem, and it may be a particle problem, or it may be a rigid body. So how do you want to practice for that? Maria, what do you think you want to do to practice solving 3D statics problems that are particles or rigid bodies?
Solve a few of them?
Solve a bunch of them, not a few, a bunch.
Solve a
So
bunch.
one, you need to know the steps. Okay, you need to know the steps. And I don't know why anybody is missing any steps anymore. You need to know the steps, right? And what are the steps? Marcine, what are the 5 steps in solving statics problems? First step is what?
Given and find.
Second step.
Your table.
Third step.
You write how many unknowns and how many equations you need.
Okay, that's in the table. Good
Okay.
though. Then?
And your free body diagram.
Great. Then?
Components.
Components and checks. And then?
Your equations and you
equilibrium equations. And in 2D problems, usually you could solve the equilibrium equations without having to do any kind of matrix, because you pick an equation that has only one unknown in it. In the 3D, it's a little harder because there's a lot more unknowns typically, but you need to know those steps and then solve a bunch of 3D statics problems. Okay? Good? All right, so that means next Tuesday, you have one problem that you're doing you have an hour to do it. Okay, and maybe we could have a little review session at the beginning if anybody has questions. How does that sound? Questions first?
You said it's going to be online. It's going to be like
Well, no, it's like no, I'm sorry, I made a mistake. Not online, it's like our regular quizzes.
Oh, I see.
It's like our regular quizzes. I'm gonna, at a certain time, the quiz is gonna open up and then you're gonna get time to do it.
Oh, so this one we're not scheduling the one-on-one meetings.
No scheduling one-on-one meetings because we can't really fit it in. Okay?
Okay.
But what I will do, already that you had one interview, and when you took the second interview, if you did better in the second interview, I replaced the first one with the second grade. So if you got a 70 and a 90, you right now have 2 90s. But if you got a 90 on the first one and a 70 on the second, you have a 90 and a 70. This one, what you get on this interview will replace the lowest one you have. Okay? So if you got a 90, a 70, and then you get 100 on this interview, the 70 gets replaced with 100, and now you have a 90, 100, and 100. Let me say it again. Interview 1, you got a 90. Interview 2, you got a 70. Interview 3, you got 100. Now the 100 replaces the 70, so you have a 90, 100, and 100. So this interview, as long as you do everything detailed, neat, and everything, you could do really well. Good? Questions on the interview?
So let's say you got a 6 on the first one.
Okay, so you got a 60?
Then you got a 7 on the second one.
Okay, is this Angel?
Yes, this is me.
Okay, so you get a 6, a 7, and what do you want to get on the third one, Angel?
I'm trying to get a 10.
Okay, so if you get a 6, a 7, and a 10, the 7 replaced the 6. So you don't have a 6 and 7 now, you have a 7 and a 7. And then when you get the 10, one of the 7s turns to a 10.
Oh, very nice.
Got it?
Yeah,
if you have a 6 on the first one, a 7 on the second one, you will notice that your grades now are a 7 and a 7 because I replaced the first one if the second one was better. So now you have a 7 and a 7, and if you get a 10, I replace one of the 7s with the 10.
Very nice, very nice. Thank you.
Practice a lot, you guys, because the 3D problems, you know, take a long time. The given and find doesn't take that long. The table probably doesn't take that long, right? The free body diagram takes a long time. Those of you who still aren't, if you have not done a lot of 3D drawings, it takes a long time to do that. Components still takes a long time with 3D problems. And then the equilibrium equations takes a fair amount of time. And then doing the systems of equations and your calculator takes a lot of time. But I'm only giving you one problem for 1 hour. Typically in statics, you get 3 or 4 problems in an hour and a half. But practice so you go through it faster. Okay, any other questions on the interview?
Are we gonna have a final or is that our final?
Yeah, no, you're gonna have a final exam. The final exam is worth, I don't remember, you'd have to look it up in the syllabus. You have a final. Okay? Any other questions? And the final's gonna be multiple choice. Or my statics final is always multiple choice. And we'll do some practice on those too. Okay, so let's go back. So today we're doing a review. Thursday and Fridays, no class. Tuesday's the interview. Thursday, December 3rd is a review again. And maybe this might be the final exam review. I haven't decided yet. On Tuesday, December 8th, in the lecture, you're doing project presentations. And on Thursday, the last Thursday of class before the final, we're doing a review. And I'm getting suggestions from you on how I should do, or Rob and I should do a better job in teaching this online environment, because we're going to be teaching statics next fall online as well, because next fall at Cabrillo is online. And then we have no class the week of on lecture of the 15th and the 17th. Your final is on Friday, December 18th from 9 to 12. And the reason that we made the final on the Friday is because if we had the final during the lecture time, your final exam would start at 7 in the morning, which is crazy. Okay, let's go to the project. You ready? Okay,
Yes.
so I'm back on today's class. Let's say review and project announcement. Okay, so project. So I'm just going to open it up in a different window. And okay. So I know people always say, you know, we always have a lot to be thankful for, and Thanksgiving is a time to be thankful. And maybe, you know, you hear it too much, but I am being really sincere. This year has been really shitty, right? For a lot of things, but there are things that we're all thankful for, and certainly family, friends. And I'm trying not to be corny, because I'm not a corny person. I'm real. But family and friends and health. I mean, you know, maybe that's another corny thing, but I'm really glad I never got COVID. I'm glad a lot of you haven't gotten COVID. I'm glad my family hasn't. Anyway, so in this time of Thanksgiving, you're going to combine statics and something that is special to you or to someone else. You have to choose an item. So the item, actually, let me just do edits as we go along, because I always think of better words when I'm with you guys. The item. So the item could be anything. It could be a part of something. It could be a product that you like. Really anything. It's just something physical, right? The item you choose must be a physical item that has at least one connection. And you know connections, pins, rollers, hinges, ball and socket joints, whatever, you know what a connection is. So you have to pick an item that's physical and it has at least one connection. And it could be something that you own, something in your neighborhood, something that belongs to someone you love, etc. It could be anything you want it to be, as long as it's physical. It has, so the criteria is 1, it's physical, 2, it has a connection, and 3, it means something to you. So I gave some examples. Perhaps a diving board if you were a diver when you were in high school. Perhaps the frame that holds your grandmother's photo. Perhaps a part of your favorite type of car, etc. Just pick something that's interesting that tells a story. Okay? Because you're going to have to tell the story. The project submittal is going to have, oh, good, 4 pages. The first page is a title page. Put your name on it, say Engineering 35 Statics Fall 2020, write connection project, the due date, and whatever title you call it. The second page, you're going to describe the significance of the item. The third page, you're going to have a large photo of the item that covers most of the page. And the fourth page has to be a CAD or a computer-aided drawing. Now, a number of you have taken AutoCAD, Engineering 25. Those of you who haven't, like Jordan, I know you haven't taken it, but you're a whiz at doing all that drawing on your iPad. So just draw it somehow, but I want it to be computer generated. So you're going to draw the item as a free body diagram, which means it's a free body removed from its connections. And you're going to show all the reactions at the supports and the common loading. I'll give you an example. I did the project. The drawing needs to have a border, which is 1/4 of an inch from the edge of the paper, and the title block. The title block needs to have your name, the date, the project title, the sheet number, and the scale. A scale, those of you who have been taken Engineering 25 might not know what a scale is. A scale is the relationship of the paper length to the true length. So for instance, if I choose a scale, and I know those of you in 25 are going to say, Joanne, that's a size, not a scale. And you're correct, but we're going to do it this way, 1 colon whatever. It means the drawing is 1/3 of the size of the real item. Okay, let's look at the grading rubric below. And here I'm going to show you my example. Where the hell is the grading rubric? Okay, I have to save this first. And then here's the rubric. You guys, this is like 10 giveaway points. This is a difference between an A and a B and a C, and a C and a D. Follow my directions. You know, I'm very detailed. I want things to be organized. Do what I say. You don't want me to take points off, and you know I will. Okay? So the title page is worth 1 point. Put all the things I asked you on the title page on it. Description of the significance. Pick something that's special to you. Why did you choose this item? What significance does it hold? Tell a story. You know, feel good during our little break. Okay. Photo of the item. I should say photo of the item. Description. You don't have to put the description here. I don't think I meant description. Now, how the hell do I edit this? I have to, oh, here. You already did the description.
So, Joanne, if it's got a connection, it's multiple parts. Does that mean multiple free body diagrams?
No, because you're only picking one item, right? When we do a free body diagram, we remove it from what it's connected to, right?
Okay, so
let's say you
your
pick-
picture frame has a hinge on it, right? So
Right.
it's got the thing and it's got an arm, right?
Right, good.
Free body of the whole thing?
So no, put your hands up the way you just had it. Remove the stand away and draw the free body diagram of the thing that's special to you, which is the frame.
Okay.
Unless you made a really great stand. Okay.
Interesting.
I'm going to say photo of item because then it's really open-ended. And then the free body diagram, you get 1 point for it being computer aided, 1 point for having the border and all the information in the title block, 1 point for the scale. If you don't understand scale, come and see me or talk to someone else. 2 points for the reactions at the supports, and 1 point for the common loading, how it's usually loaded. So a picture frame, how is a picture frame loaded? Besides the stand, Dave?
There's weight and there's normal if it's sitting on a
Weight and
counter.
normal.
Yeah.
That's it. Okay. Okay. And you could ignore the weight. You could just put the normal. Okay. So you see that, like, putting a border on and the title block's worth 1 full point. So make sure you put all the things I want in the title block. You want to get that 1 full point. Okay, let me make sure I saved it. Okay, so now let me show you my example. And I'm going to enjoy showing this to you. Because, I mean, it's stressful here, but I'm enjoying, this made me have enjoyment doing this. Okay, so here's the title page. Can everybody see this or no? Probably
No.
not.
Hasn't loaded yet.
No, it's because it's a
And share
because
the other
it's
window.
a PDF. So let me load it. Okay, could you see my title page? Can you see it?
Yeah, that's good.
Okay. Name, fall 2020, engineering 35, connection prior. I'm following my own directions. Exactly. Okay. All right. How do I get this bigger now?
It's a good size. We can see it.
Yeah, but I'd like to take the whole page is like stuff over here that I don't, oh, close here. Maybe I could close this. Great. Okay. So, okay. So what I picked was my mom's front door. Okay. So I chose my mom's front door. Do you want to read it? Or do you want me to read it to you? I'll read it to you. I chose my mom's front door because this is what, you know, I'd rather you not read it when you're presenting it, but I chose my mom's front door because it was my childhood home, because it is from my childhood home. And more importantly, it has a historical significance. On the next page is a photo of my mom's door. And here's the photo. Let me make it smaller. So it's like an old-fashioned door, but what's so important, what I love is this. You guys can see it all? It's a stained glass window that has a design in it. So now I'm going to go back. You'll notice that there's a stained glass on the door. The image on the stained glass is of 2 modernistic, this was at the time in the 60s, temporary structures designed and built for the 1939 World's Fair in Flushing Meadow, Corona Park. The structures are referred to as the Perisphere and the Trilon, and together they were the symbols for the 1939 World's Fair. Both the Perisphere and the Trilon were built with a steel frame and plasterboard facade. The periscope was 180 feet in diameter and the Trilon was 610 feet in height. Figures 1, 2, 3 show the construction, the location in the fair, and a model of it. So here's the construction of it that happened in the 30s. And this is what the fair, this is a photo, an aerial photograph of the fair where the periscope and the Trilon are. So they were pretty big. And then this is a model. Okay. All right. During the 64-65 World's Fair, boy, I have 3 errors in here so far. I forgot to put a space between 610 and feet. I forgot to put an N in the and now I forgot to write fair. During the 64-65 World's Fair at Flushing Meadow, Corona Park, a Unisphere was constructed in the same location of the Perisphere and the Trilon. Unisphere is a symbol of Queens, which is where I'm from. It's part of New York City, and it still stands today. Whenever someone visits me in New York, I take them on a walk to the Unisphere. I love the Unisphere. It's a steel structure layered to show the topography of the continents. So I have a small picture here. If you're able to zoom in and look at different ones, you'll see that there are steel layers on it to show. So this is South America, and you could see the Andes Mountains. It has a relief in it. It's showing the topography of it. And there's a big fountain around it. And what's also cool about this that I didn't write, but I was born in 66 in January, and my mom was walking around the 65 World's Fair when she was pregnant with me. And I have brought some Cabrillo folks here. Tony Kakachi was a past student who wound up lived in Manhattan for a while, and I took him here. And then Roxanne and a couple of other engineering students came to teach at my high school, teach at girls in engineering camp at my high school, and I brought them here too. Okay, Flushing Meadow Corona Park is also the home of the annual US Tennis Open, where I was a ball girl in 1984 when Chris Evert played Martina Navratilova and Jimmy Connors played John McEnroe. Some of you probably don't even know who these people are. And it's home to the Queens Museum, which housed this amazing three-dimensional panoramic of New York City, and a Tiffany stained glass exhibit, which was donated to the museum because the Tiffany factory was in Corona. So this right here is where the Tennis Open is in the same park. And this is this 3D panorama. So you can see it's quite small because there's a guy standing on it. But so this door means a lot to me, or anyway, so now you get the idea of what I want. I want you to kind of step away from school for a while and think of something that's significant to you and just write about it. Here's the picture of the door. And now here's the statics part. Again, it's small. I took the door, I drew it, I dimensioned it. There's a hinge here, here, and here at point A, B, and C. So I drew the three forces that are reactions at the hinges. I also drew the two moments around the Z and the X axis, all of them. And then I showed the load of the door, pushing the door open. It could have been a pull, but I put it push. And now if you look, there is a border, 1/4 of an inch from the outside of the page. And there's also, let me zoom in. Here is, it doesn't look so good on what I'm showing you, but it's supposed to have the title of it. It's supposed to say drawn by, and my name, the scale of the drawing, the date, and the sheet number, 1 of 1.
I
Okay,
thought you would put in
questions on the
door-themed
project.
O's on your mom's door.
Jason, what?
It looked like you put in door-themed O's on your.
Yeah, I'm on a computer, I'm on my laptop here that I don't have AutoCAD. So I had to draw it and then bring it in, and it doesn't really look good, but yeah, that's pretty good. But I didn't mean it to be that. It doesn't look so good, but that's the only thing I could do here.
It looked on purpose. I do have a question, which is about now, which certainly will come up. How can students access this program? What do you use?
You mean AutoCAD?
You can get it for free with a Cabrillo student ID.
Thank you, Dave.
There's
you
like
can
a free
get
student
AutoCAD for
version.
free, but you can draw it on, you don't have to use you don't have to use CAD. Use Paint, use whatever stuff they have on your iPad or your laptop or whatever. I just want it drawn by a computer and not by hand.
Okay. Yeah, the problem I've run into with the student ID is it's so out of date. Like, a picture of it looks like it. I haven't been to school in a year.
You don't even need a student ID. If you just go to Autodesk, their website, you don't need an EDU email or anything. It's really easy.
I think you just click that you are currently a student at Cabrillo College, and then you get a code.
Okay.
And Jason, you're just asking about the drawing, right? You're not asking about the rest. The rest is just a Word document.
Right.
Okay. All right. Any other questions about the project? So the intent is for you to realize that, yes, statics is in your everyday life, but the main idea is to give you kind of an extra credit and to have you just think about something that's special to you. I'm going to stop.
I had another question.
Yeah, Angel.
How is that AutoCAD drawing going to be graded? Is it going to be graded like an AutoCAD final assignment, or is it going to be graded like if it's there, it's there?
Good point. It's not going to be graded like an AutoCAD assignment, but everything needs to be dimensioned, right? Mm-hmm. So let's see. Let me go back to the picture. So notice that I did make sure that everything was dimensioned, right? The total width, the total height, the total width is dimensioned. I dimensioned the other pieces. I didn't actually follow all of ANSI standards because notice normally for ANSI standards, there should be the total dimension and then just two others, and this should be blank. So I followed ANSI standards here. I followed ANSI standards here. I left this blank, but notice here I did all three of them. So I'm not necessarily following ANSI standards, but make sure it's dimensioned and make sure it's drawn to scale.
All right, sounds good.
If I print it out, I better have the scaling right.
All right.
The scale is so important, so you need to know it anyway.
Wait,
Okay,
how would
well-
you have done that left side differently?
Say it again. I would leave one of them out.
But then it'd be underdefined because you don't know the distance from the top hinge to the top of the door.
On the other
Oh,
side,
no,
you
I
do.
did leave one out.
Yeah.
You did.
I did leave one out. I did follow ANSI standards.
There you go.
Woohoo!
Wow.
Okay. All right. Any other questions on the project?
What I have a question about the whole connection piece. I'm thinking of an object that has a lot of internal connections and stuff like that.
Okay, let me stop sharing for a minute. Okay,
But I don't know. I'm thinking of a raft frame that sits on a raft, but I'm not sure if that has like
a
external,
raft like in swimming?
like a raft as in like a rafting, yeah, like a boat with a frame on it.
Rafting with a frame. You mean a raft, R-A-F-T, in a boat?
Yeah.
So you're thinking about a raft and like, because there's so many connections.
Yeah.
Okay, I got it. So what you want to think about, because there's like loops and carabiners and all that kind of stuff. Is that what you mean?
Yeah, but
Just
also
pick some.
okay, but if I use it as a whole, all of those would be internal.
Oh, yeah. No, well, you could it would be like taking it off.
Okay, and I could also do the connections of where it's strapped on, I guess.
Sounds good.
Okay.
I'm going to be very flexible with this. But if you need, like, obviously the door was easy, right? You guys looking at it knew it was a hinge. Well, I'm going to need to know what it is, right? So maybe there should be maybe I should require a little description. You know what? Maybe I'll do that. I'll add that to there, that on the bottom of the free body diagram or somewhere, maybe on the, maybe where the photo is, because you don't need to have the photo that big. Maybe I'll have a short description that says what the connections are and what the, yeah, I got to do that. Let me add it. So I'm going to tweak my project a little and tweak the project description.
So
Okay.
I guess for something like for a strap, would it be comparable to a ball and socket? Because it has,
I would say with the strap, I would use the strap as the loads on them.
okay.
Let's talk offline about that. Okay.
Okay.
All right. But I basically need to have a description of the connections because otherwise I may not know what connection it is. Okay. All right. Let's go back to the course overview. Okay, so you know what the project is. You know, a week from today is the interview. You have a quiz that's going to start in a little bit. So let's look at the overview. Okay, so let's start with the steps in solving the problem. And we already said what they are. Let me. Okay. Okay, everybody can see these steps now, right? Make them bigger. Okay, so I'm going to just write some, actually, let me do it this way. I'm going to go to Word. Okay, I'm on a Word document. Can you see it?
Yeah, but that looks worse. There's all like the paragraph symbols and stuff.
Oh yeah, let me get them off. I love them, but I know they're irritating to look at. Better?
Yes.
Okay. Okay, everybody's fine. Given, you always write sketch info and then you write any information that's given that's not in the figure. No problem. Fine. Sometimes you guys, rather than writing reactions at A, sometimes you guys write reactions at A. Instead of writing that, rather than writing, write, you know, what it is, AX, MAX, you know, write what the unknowns are. Because that'll clarify for you and everybody else that's reading it what you actually are looking for. Okay? Everybody good? I'm going to move on. Okay, table. And I mean, I didn't take any points off for that. I was just a lot of some of what, when I was conducting the interview 1 and 2 were actually kind of some teaching too. So table, identify all the forces in the systems, including the reactions of the supports, and determine what forces and moments, magnitudes, and directions are unknown. Everybody's pretty comfortable with that. And some of you though did need to be reminded that for a 2D body, if it's a rigid, then, okay, for each there are, for each rigid body, how about if I wrote, for each particle, here, correct me on this. So Marcine, did I ask you a question yet?
Yeah, you did.
Okay, Mackenzie? Luis? For each particle, how many equations do you have when you do statics of particles? Do you have 3 equations? Luis? Liam?
No, you only have 2 equations.
Thank you. So these are the only equations, right?
Yeah.
Right. So, okay. And then, but for a rigid body, there are 3 equations, right?
Yes.
So let's move this up here. So for every 2 unknowns, there's 1 body. You need 1 body if it's a particle, right? And if it's a rigid body, then if you have 3 unknowns, and I'll, because I'm editing our sheet that we worked from already, I'll post this.
No friction on this one?
No friction. Good question. So let's say, and we only saw friction problems if it was a 2D body, right? So let's add that. Good. For a friction problem, there is 1 more equation. Great. And that's F sub S equals, oh my boy, I have to, you know, I'm just going to write, how do you spell nu? N-U? I'll add it later. Normal. I'll put S as a sub and I'll put whatever the correct symbol is rather than doing it now. So that means you have 1 more equation. So then it depends on whether it's, we've never seen them really as particles with the friction problems. So for every 4 unknowns, you only need 1 body. Everybody good with that? Thumbs up? Okay, so then the next, select the body to analyze. If all the forces on the body are acting concurrent, then it's drawn as a particle. But if the forces on the body are not concurrent, the body needs to be drawn as a rigid body with dimensions. Some of you forgot dimensions. Don't forget things like that. I just take points off. You got to have it. Because forces acting at different points on the body create moments. Draw the free body diagram. So what do we need to have in a free body diagram? So Laura, What do we need to have on a free body diagram?
You need to have the axes.
We need to have the axes. Okay, what else do we need to have? Forces labeled. And they could be labeled with a variable or the value of it. We also need force directions shown. And the directions are shown with a line, an arrow, but also with either distances or an angle, right?
Yes.
Okay, so if distances are given, we use ratios to find the components, right? If an angle is given, then you use an angle. What are you finding is most common? Laura, you want to answer that? On most problems we get, are you finding more distances or angles?
Recently, distances.
Distances, why? In engineering, everything is a distance, right? A rod has a distance, you know? Distances are more common. Angles are more common in math. You know, so most problems, we're going to see distances all the time. Okay. All right. Next step is to do, is the components. So during the components, let's write components and checks. A number of you forgot to do it. Maybe you don't like to do them, but I like them. And if I like them and I'm your boss, you got to do them. And it's crazy not to do them because you could spot an error way before you do a whole problem. I mean, I'm sure you have at least every single one of you have had to catch one error already in your component check. I mean, maybe you haven't, but I would bet money that 80% of you have found an error already in your checks. Whether it happens to be the value, probably more often than not, it's a negative or a positive that you messed up on. Okay. After that, you do your equilibrium. Okay. And for each free body diagram, use the equilibrium equations to solve for the unknowns. And to simplify the problem, solve the equation first that has one unknown in it. If you find the equation that has one unknown and you solve for that unknown, and then you move on to the next equation and the next equation, odds are you're going to have less errors than if you do a zillion equations and plug them all into your calculator. You're going to make a mistake. I mean, in statics, the main thing we're trying to do is prevent errors. Okay, so I'm going to save this. I'm going to stop sharing. And what questions do you have regarding the steps?
I have a question.
And what is that question, Jason?
Oh, well, in Trusses, we're
going to Trusses now. Hang on. Let me go on to Trusses and frames, and then I'll answer your question. Thank you. I'm going to go back to Trusses. Can everybody see the truss overview page? Remember, in front of, at the start of every module, there is an overview page. So we already, we did this review at the beginning. All members in a truss are two force members, right? And actually, let's edit this. All members in a truss are two force members, which means there are two locations where forces and or connections are located. So it has to do with location, number of locations, not the number of forces. So maybe they chose the wrong name for this. Maybe they should have called it two location members, but some guy, probably a guy, made the name two force members. And I'm not saying guy to put down guys, I'm saying a guy because in history, most things were recorded as a man discovering it. Are you guys okay with my little feistiness today?
Yes.
Okay.
That's fine.
You're really on one today.
Today, Joanne.
Wow, thank you.
Just flowing.
Okay, is the accent coming out too? All right. So
Yeah.
all members are in a trust are two force members, and we know their internal forces act along the axis of a member. You got to know that. Okay. Most importantly for frames, because it reduces frames. Frames have so many unknowns in it. The biggest thing for trusses that you want to know are the zero force members. Now, why would somebody call us two force member and a zero force member? Because a zero force member sounds like there's no connections and no forces, no locations at all, but a zero force member has no force. So this one makes more sense. Zero force means no force. And on the quiz, which I haven't graded yet, there were so many on that trust quiz last week that were zero force members, and it simplified the complicated problem to a very simple to a simpler problem. And remember, there are two rules, and remember those rules. And then you have two ways of solving for forces in a truss. One is method of sections, and one is method of joints. In both cases, you first find which members are the zero force members. Then the next one is to separate the whole structure from its main supports and determine the reactions of the supports. And then this is where sections and joints differ. Sections is you break the truss at the place that you want to know the members. And for the joints, you got to go through every single joint. And typically there is a check for both. At the end, the last step in both of them is always to put a T or a C if the member is in tension or compression. I'm going to save this, excuse me, because I just edited it. Okay, Jason, you had a question about a truss. Did I just cover it or do you still have it?
Well, yeah, so I guess I wonder when you would like us to really break things down into components separately and do the checks, and when it's appropriate to combine them into
Okay,
the
good.
delivery.
Good point. Okay. Edit.
thing.
I'm going to edit again. For, hang on. For both methods, you do not have to solve for components. Okay? Because it would take forever to do that for all. I mean, in sections, there's usually only one or two. Maybe we should say just in this one. I'm okay with you skipping it. For both methods, you do not have to solve for components or checks. You can go straight to the equilibrium equations. Is everybody happy on that?
Right, but for example, if the interview on Tuesday or whatnot is on a statics of rigid body, you know, we're back to doing components separately, yeah?
Right, this is only for trusses.
Mm-hmm.
This is only for trusses. Okay? Good? Because otherwise you look at a truss and we have all these angles. We're going to be doing, I'm trying to decrease the amount of error. If you spend all that time doing all these components of the truss members, you're bound to make an error because it's going to become a pain in the ass. So there's no reason to do components for this, okay? And this, of course, is my opinion, right? Any other questions on trusses? Okay, so now let's look at frames. Okay, frames. It says, the introduction to frames says, you already know how to solve frame problems. They're just like solving other rigid body statics problems. Frames are structures that consist of at least one multi-member. So if you have Jordan, if you have a structure that has a zillion 2-force members and it has 1 3-force member, is it a truss or a frame?
It's a frame.
Thank you. Okay, frames and trusses are similar, but trusses have only 2-force members. Okay, so in the frame overview, that's where I talked a lot about 2-force members and 3-force. It's defined by how many points on the member that the external forces and reactions are located. 2-force members with pin connections, the 4 unknowns reduced to 2 unknowns, to 1 unknown. So for analyzing a frame, the first free body diagram is the free body diagram of the whole structure. The second free body diagram is the free body diagram of the member in question. Typically they say, I don't know what you guys are chatting about, but there's a lot of smiles. Free body diagram of member in question. Usually they're asking, find all the unknowns in member ABC. So you're going to do ABC. And then you may have to do a third free body diagram. Okay, so now process asking for all the reactions at the supports. Give and find, determine the number of unknowns from the table. And then, so let me just keep going for here. So in this case, if they're asking you for all the reactions at the supports and all the forces, then do the table, because then it allows you to find out what the total amount of unknowns are. But let's say they're just asking you to find an unknown in only 1 or 2 members. Well, you don't have to do the table, because the table, and you guys are really good at this. With the frame problem, almost all of you said, I like to do the table because it allows me to identify all the unknowns, but I realize that I may not need to find all those unknowns. You were really comfortable with that. And some of you said, I'm not going to do a table because I know I only need 3 unknowns. And if I do a table, there's 20 unknowns. So you were really, comfortable with the whole idea of whether to do a table or not with frames. Okay, questions on any frames? Isaac, did you? Frame question, anybody? Okay, I'm gonna stop sharing. Okay, actually, no, I'm gonna go back to share, to just go back over. So today. So we looked at the steps, we looked at the overview of the trusses and overview of frames. Remember, these overviews are at the beginning of the truss and the frame module. When I get the recording, I'll post it. You know what the project is, you know what the interview is. Lastly, and there's a quiz today on shear and bending moment diagrams. It's not a long quiz. Well, no, it could take, it depends. How much practice? I'm not giving you that many problems to do. And by the way, the shear and bending moment diagram problem 89, if you look back, it said that problem was very complicated. I should have never picked it, and it's optional, and don't worry about it. Okay. However, I am adding another homework problem. Take a look at this. Not a problem, a homework. I have a video lecture. It's on centroid, center of mass, and center of gravity. And you already have done this in calculus and probably maybe even in physics too, where you're trying to find the center of mass of stuff. But in engineering, the important thing is finding this, because as engineers, we design something that has more than one thing. This calculator. Boy, I'm not getting it apart. Little comic relief for you guys. There, got it. It has a front plate, it has a back plate, it has pieces inside. If I wanted to know the center of gravity of this is what I'm referring to as a composite body. It has a whole bunch of parts in it that are connecting, all these buttons. I could find the center of gravity, the center of mass, the centroid of this. Okay, so I made a video Here's the video lesson. It's not as long as typical, it's not as long as a class. It's maybe only 20 minutes long. Here's the video right here again. So I probably should put it up here as, let me add this. Okay, so your homework is, let me put this one first. Let me publish it. Let me indent it. So you have to complete complete the centroid, center of mass, and gravity module below. Okay, and you'll see that when is it due? Something's due the 27th. Watch the video by the 27th, but the homework is really due by the 30th. So you have a week to do it. Okay. All right. So homeworks, complete that module. This is the last topic we're doing in class. Here's the project. Here's the interview. Remember, it's a 3D statics problem. And I'm ready to move on to the quiz unless people have any, you guys have any questions.
What's your favorite kind of pizza?
Extra cheese.
No, but like New York pizza or Chicago pizza
New
or
York.
California pizza.
Oh, New York pizza, extra cheese.
What makes it New York pizza?
You know, Pizza My Heart is the closest, but
Okay.
the pasta sauce is a little different.
Their prices are criminal though.
Yeah, yeah. Okay, we should go on to the quiz, right? You know what? I need to look at attendance because attendance. So let me stop sharing. Let me see who's here. Okay, Amani here, Angel here, Bon here, Colin, yes. Daniel C's here, yeah. Daniel Hall.
Here.
Okay. Danny's here. Dave is here. David, LR here. David?
Here.
Great. Edgar's here. Elizabeth, yes. Elizabeth?
Here.
Okay. Eric?
Here.
Gerardo? Yes. Hyoji?
Here.
Great. Isaac? Jack?
Here.
Okay, Jason? Jason Lee?
Hi.
Hi. Jordan's here. Laura's here. Liam, you were here, right? Liam?
Yeah, I'm here.
Okay. Luis? Yes, here. Thank you. Luis, sorry before I had to skip over you. I didn't know you didn't have a voice. All right. Marcine? Yes?
Yeah.
Maria, Matthew, Myra, Miles, Peter, Tim, you guys I called on. Mackenzie. Okay. All right, you guys. So the quiz is open. Go for it. And I'll change the time because I took up some extra time. So you need another 15 minutes. So I'll go in and change it.
Thank you.